Hey everyone, welcome back to Robotics. I hope you guys are doing well. Today we have our 12th lecture, and again we'll be talking about Jacobians. So to get us started, I've got a video, and this is a video of a robot that's been trained to do a variety of different household tasks. And now we want to test what the robot's learned by seeing how it can fold laundry. I think there are a couple different interesting aspects here, but one of them is the way the robot has to manipulate the clothing items. It needs to be very aware of what it's grasping, how it's moving its end effectors, and just how it manipulates the clothing itself. In order to do this, I want to make sure I understand the velocity relationships for my robot. As I move the different joints of my robot, in what direction is the end effector moving? How quickly is it moving in that direction? And all that goes back to the Jacobian. So in today's lecture, I'll show you a kind of a step-by-step example of how we can find the Jacobian matrix for a serial robot arm. To get us started, I just want to review the main steps for finding the Jacobian. And again, if you haven't already, I'd encourage you to watch the previous lecture. So let's get started with just a quick recap of what is the Jacobian. Now, the Jacobian is a matrix that maps me from my robot's joint velocity into the linear and angular velocity of my robot's end effector or another point of interest. The idea is I can measure the velocity of each of my joints, and now I want to understand, all right, if I'm moving my joints with this velocity, how quickly is the end effector moving and in what direction is it moving? The main steps for finding the Jacobian is first, you're going to want to find the screws for each of the different joints. And those screws describe the axis of motion for those different joints. Next, you'll want to find your forward kinematics and then extract from your forward kinematics the position vector. This position vector will be used along with the screws in the formula you see at the bottom of the slide. And this is the key formula that we have derived for finding our Jacobian matrix. All right, so a couple additional steps I want to mention. First, in the practice set 12, that's the practice set from the previous lecture, we actually implemented a Jacobian function in MATLAB. So I'll call that in today's lecture, and if it makes no sense, I'd encourage you to go back and just check out that practice set. The idea for this Jacobian is going to take in my initial transformation matrix, my screw matrix, that's just all the different screw vectors put together into one matrix, and then my joint position theta, and it's going to output my 6x(n) Jacobian matrix. Good. Another note of interest is, in my examples, I often mention finding the Jacobian to the robot's end effector, and usually that's what I want to find. But there are times when I'm interested of the Jacobian for another point just along the robot's arm, not necessarily the end effector. And actually, it's pretty straightforward to find the Jacobian to an arbitrary point along this kinematic chain. And what you're going to do is two steps. First, you're going to pick that point you're interested in and just assign a coordinate frame to that point. Find the initial transformation matrix from your spatial frame to that coordinate frame of interest and call that t of 0. So you'll set t of 0 equal to that new initial, or maybe you can call it the home transformation matrix, to that specific point of reference. Then the second step is you're going to take all your screws, and every screw that comes after that point, you're going to set those equal to 0. And the idea here is, again, I'm just using my own arm as an example, and let's say I'm interested in some point here. I don't care how the wrist is moving, like the speed of the wrist in the different direction. These screws don't have any impact on my velocity at this point right here. And so for all my screws that come after my point of interest, I actually don't include them when I'm calculating the Jacobian matrix. So set all those screws just equal to 0. And if you do those two steps, you can apply the same formula as we had before, and you'll find your Jacobian for your point of interest. All right, the last note, and this one's just pretty practical. If you're doing this in MATLAB, there'll be times when you want a numerical Jacobian, and there'll be other times when you want a symbolic Jacobian. If you want to force a symbolic Jacobian, what you can do is you can set this matrix S just equal to sim S, just declaring, hey, I want this to be a symbolic Jacobian. These should be symbolic variables. So if you're having some trouble forcing it to be symbolic, use this trick, and that should solve it. And then again, if you don't want it to be symbolic, you want it to be numerical, make sure you don't have any symbolic variables anywhere within the definitions of this Jacobian, or else it's going to be a very slow and cumbersome process. If you're expecting something numerical, but you're actually getting something symbolic. All right. So with those kind of practical tips out of the way, let's practice finding the Jacobian with an example. So in this example, I've got a 2-link robot arm. Here's going to be the ground right here. And I've got my spatial frame that's connected to the ground. The y-axis is pointing up, the x-axis is pointing to the right, and the z-axis is coming out of the screen towards you. My robot's got 2 different joints, so it's a 2 degree of freedom serial robot arm. This first joint is a prismatic joint that's extending upwards, and this second joint is a revolute joint that's rotating around positive counterclockwise. It's coming out of the screen towards you. And then I've got another link of length L, and then I'm going to have my end effector right here, and that's going to be my point of interest. So in this example, I'll be trying to find the Jacobian matrix for the robot's end effector. If you want, you could pause the video right now and see if you can find the Jacobian for the robot arm. If not, we'll go step by step together. So our first step is we're going to need to find the main components that we normally would get for our Ford kinematics. This includes my home transformation matrix and then all the different screws for my robot arm. So just looking for my home transformation matrix, I'm going to look at the transformation matrix from S to B when the robot is in its home configuration, and that's what's shown right here. Remember that in your home configuration, theta 1 and theta 2 are by definition equal to 0. So this home transformation matrix is like what you see in this slide. This is a valid transformation matrix with rotation, position, zeros, and then 1. For my rotation matrix, I've set its identity, and that's because each of these axes are aligned. The x-axis in the spatial frame lines up with the x-axis in the body frame, and the same is true for the y-axis and the z-axis. So I've got an identity for my rotation matrix. Then for my position vector, I move up L units, and then I move to the right L units, and that's how I get to the point here at the origin of my body frame. Now, you might stop the video and be like, well, it should be L plus theta 1 units up. That's a common mistake, but it's a mistake. And the reason why is because when the robot is in its home position, when I'm trying to find this transformation matrix, remember that theta 1 and theta 2 are both equal to 0 by definition. So yes, it is L plus theta 1 up, but since theta 1 is 0, it's just L units up. All right. So just hopefully you caught that when you were doing the work yourself. All right, so that's my home transformation matrix. Now I need to find the screws. Now my robot's got 2 joints, so I need to find 2 screws. This first joint is a prismatic joint. The second joint is a revolute joint. And here are the appropriate formulas I need to use to find those screws. For my prismatic joint, I know the top 3 elements, the angular elements, are going to be all zeros. So I'll have 0, 0, 0. And then the bottom 3, that's just a unit vector pointing in the direction of positive translation. This guy is translating positive upwards, so it should be something pointing in this direction. All right, for my second joint, that's going to be a revolute joint. The main thing is I need to find this omega s hat, and that's a unit vector pointing in the positive direction of the axis of rotation. So this thing, it's rotating counterclockwise positive. If I look at my coordinate frame and use my right-handed rule, I line up my thumb, and I realize, oh, that's lined up with the positive z-axis. So this guy is rotating around the z-axis. I also need to find P. Now that's just a vector from S to this joint. And so I'd have a vector that starts off at the base right here and goes up to this joint. Remember to find that vector when the robot is in its home position. All right, so we've got the rules. Now let's go through the process. And this should seem pretty familiar. It's the same process we went through with Ford kinematics. So finding our first screw, I realized, yep, it's 0, 0, 0 on the top because there's no angular velocity for this prismatic joint. And the bottom is just 0, 1, 0. And that's because it's translating upwards. That's lined up with the positive y-axis. Great. And again, I'm looking at everything with respect to my spatial or world frame. You don't need to worry about the body frame when you're finding these different terms. It's only relevant when I was finding that home transformation matrix. All right, so I've got S1. Now I want to go and find S2. 2 different elements. First, like we mentioned, I know that I'm rotating positively around the z-axis coming out of the screen towards you. So I'll have 0, 0, 1 for my omega 2 right here. Then this vector from S to this joint, it's going to be L units up along the y-axis, so 0, L, 0. Don't make the mistake of doing 0, L plus theta 1, 0, because again, theta 1 is 0 when I'm in my home configuration. And if I use the appropriate formula, this one right here, I can find that S2 is 0, 0, 1, L, 0, 0. So that'll be my second screw. All right, now I've got this home transformation matrix T of 0. I've got my 2 screws, and I'm ready to apply the Jacobian function that we got in our previous practice set. Now, like you probably noticed, and I've mentioned before, when you're getting the Jacobian, you're just doing the exact same steps as you would do for the Ford kinematics. And that's kind of a nice advantage of this method because you need both anyway. You need your Ford kinematics to know where the robot is, like where is its position or orientation. And you also probably want to understand the velocity relationships that come from the Jacobian. So all you have to do is just the same things, find these screws, find your home transformation matrix, and you can get both the Ford kinematics and the Jacobian at the same time. So a nice advantage of this approach. So here's my code in MATLAB that I use to find this robot's Jacobian. And in general, this is something you're going to want to do in MATLAB or another programming language. So first, I declared my symbolic variables. My first symbolic variable is L, and that's for my link lengths that you see right here and right here. I just said, hey, that's a real number, so I have the real right here, so it's not a complex number. Next, I declared a symbolic 2x1 vector for theta, so it'll have two elements, theta 1 and theta 2, and this is my position vector. And again, I declared that these are real, these are not complex numbers. Okay, next I inserted what we've already found together in this lecture. I put T of 0, that's my home transformation matrix with identity for rotation, L1 units to the right, L units up, and then 0 in the z-axis. So this is my home transformation matrix. I've got my first screw, and then I've got the steps for finding my second screw where I've got omega 2, P2, and then I got the formula at the bottom where I got omega 2 bracket of P2 times omega 2, and that'll give me my screw S2. Once I have these, I'm ready to apply my Jacobian formula. So I'm going to take in T of 0, S1 and S2. I'm just putting those together into one matrix, call that S if you like, and then theta on the right, and that'll be my Jacobian formula that we found in the previous practice set. And this is just a straightforward implementation of what you see on the right, and this is the formula that we found together for a Jacobian matrix. I'll get out a symbolic value, and I want to simplify that to get the cleanest form, so I'll just use simplify in MATLAB to get some sort of shorthand or clean answer. If you run the script yourself, you should get the following answer. So I get a Jacobian, and let's first talk about the dimensions. Now this Jacobian, it's a 6x2 matrix, and that makes sense because if I look at my robot, it's got two different joints. So I should have a 6x(n), or in this case, 6x2 matrix. Great. Now, to get a little intuition on the Jacobian, I want to try multiplying this Jacobian by my joint velocity. So what I'm going to do is I'm going to take the Jacobian I just had and multiply it by theta dot. And I'll get this answer, right? So this is telling me the linear and angular velocity of the robot's end effector with respect to my spatial frame. And again, this is supposed to be the intuitive velocity that makes sense to us. Let's see if it actually does make sense by looking at the diagram right here. And what I've done is I've split the robot into two parts. In the first part, I'm going to assume that this second joint is fixed in place, it's not moving, and I want to see what happens when I actuate my first joint. So when I increase my joint velocity theta 1 dot, what happens? And the same idea is true in the second diagram. Here I've locked my first joint in place, and I'm only going to actuate my second joint. And so I want to understand what happens when I have some velocity theta 2 dot. All right, so let's start with the first one, and let's imagine theta 2 dot is 0. I'm only looking at theta 1 dot. Well, if I look over here, this term will be 0, this term will be 0, this term will be 0, and the entire twist V simplifies down to 0, 0, 0, 0, theta 1 dot, and 0. If I look at my drawing, that makes a lot of sense because what it's saying is that the end effector, if I actuate the first joint, experiences a positive linear velocity in the y-axis, and that's the only velocity we experience. Makes sense to me because we know the y-axis is pointing up. I move this prismatic joint, it moves upwards. Great. So that part makes sense. All right, let's talk about this second joint. So I'm locking my first joint in place. We're not dealing with prismatic. We're only looking at the revolute joint now. And intuitively, I know if I rotate this revolute joint, my end effector is going to trace a circle around this point, right? So I kind of know mechanically what I expect to see here. And then instantaneously what the velocity should be, the linear and angular velocity, my angular velocity should be around this z-axis coming towards us. And the linear velocity should be pointing tangent to the circle. In this specific joint position, it should be pointing upwards. All right, so let's see if the math reflects that. First, let's talk about the angular velocity. So my angular velocity is going to be 0, 0, theta 2 dot. That makes sense. This thing is rotating around the z-axis, so it has an angular velocity that's strictly in the z-axis. Seems good to me. Now for the linear velocity, like I said, I'm tracing this circle in position, I'm taking the tangent of that to find my linear velocity, and that's what you're seeing right here with a radius of L. So if you look at this specific point, when the robot is at this configuration, my linear velocity should be pointing straight upwards. Sine will be 0 because it's at 0 degrees, and I'll just be left with L theta 2 dot, and this will be 1. So I don't know if that all makes sense immediately, but if you look at this yourself and just kind of go through these steps, hopefully you can convince yourself that yes, this linear and angular velocity kind of matches what I would expect for this specific robot arm. All right, and that's a great example of how you can find the Jacobian matrix for one of these robots. If you'd like to practice a little bit more, I encourage you to go to the practice set. You can find it attached either in the description or in the pinned comment. As a reminder, the first page has the questions and then the following pages have the solutions so you can check your understanding. In the next lecture, what I want to do is kind of break down this Jacobian matrix and see if we can get a more intuitive understanding of the elements of that matrix and really what it means for our robot. So I look forward to seeing you there.